So we will continue with the second case, the complex roots. I'm going to leave the double real root at the end because, again, I want to prove that case, to show how the formula comes to be. This complex case, I'm going to just give you the formula and I will skip the proof. It's given in the book. It's not that long. I'll just give you a little bit of overview why the solution looks so different than in the real case. But let's review what we just did last time, right? So whenever you try to solve an equation in that form, again, linear, second order, homogeneous with constant coefficients, your starting point is setting up this characteristic equation and solving for r. Because again, you're looking for solutions in the form of exponentials. So if the quantity under the radical is strictly positive, you have distinct real roots. And the solution looks like that. We had an example in the previous part of the lecture. Let's do the opposite case now when the quantity under the radical is negative. Right? So the square root of a negative quantity, that means the roots are complex. In that case, your formula for the solution depends on the real part and on the imaginary part. So your first thing to keep in mind is to write your r, your solution, precisely in this form, real part plus minus I times the imaginary part. So remember, I is the shortcut or the notation for the imaginary unit, right? Square root of minus 1. So if you have any fraction here, you must eliminate it so that you can write clearly what alpha and beta is, which is the typical notation for the real part and the imaginary part. So in this case, one can prove that the solution can be written like this: e to the alpha t, quantity c1, cosine of beta t, plus c2, sine of beta t. So you may wonder, why does it look like that if you're looking for exponential solutions? Well, this has to do actually with the Euler formula, or the complex exponential, which states that e to the I times x is cosine of x plus e I sine of x. So the complex exponential can be expressed in terms of sine and cosine via this formula. You don't have to memorize this one, but this is the reason why eventually the solution looks like that. There's a little bit more behind this than what I just said. What you have to understand is that, again, just like in the real case, you have two distinct solutions, two distinct r's. So you have two distinct exponentials in that form. But you want to provide a solution space in the real case. So you have to basically manipulate those two independent solutions so that you end up with solutions in using real numbers, so that you don't have any I here. So you can look in the book to see how that comes to be, but you can show that with some linear combinations of these complex exponentials, you end up with a linear combination in that form, which is the general solution of your ODE. So the two independent solutions, y1 and y2, are in fact e to the alpha t cosine, e to the alpha t sine. We keep the e to the alpha t on the outside because it's more compact this way, but even in the complex case, the structure of the solution is the same, right? A linear combination of two independent solutions. So let's go on with one example in the complex case. And this time let's actually write down an initial value problem maybe. So suppose y double prime minus 4y prime plus 5y equals 0. And like I said, in the second order case, you need two initial conditions. So y of 0 equals 1, let's say, and then y prime of 0 equals minus 2. Notice that the initial conditions in the second order case are typically given in that form because, well, I mean, if you want a practical justification, it's like you are given a displacement and a velocity to begin with. So imagine, for instance, that y of t is a displacement of an object. This will be like an initial displacement. This will be like the initial velocity. So our characteristic equation is r squared minus 4r plus 5 equals 0. And using the quadratic formula, we get that r is minus negative 4, which is 4, plus minus square root of b squared, which is 16 minus 4 times 1 times 5. So that gives me 4 plus minus square root of 16 minus 20 over 2. And that's minus, or 4 plus minus square root of minus 4 over 2. So you have to pay attention with the computation here, especially if you have complex numbers. Minus 4 under the radical becomes 2i. And then you must distribute the denominator. Remember, your goal is to write your r in terms of the real part plus I times the imaginary part. So your r in this example would be 2 plus minus I. So alpha will be 2, beta is 1. Real part, imaginary part. So once you're done with this, again, according to the formula, y would be e to the 2t, alpha is 2, c1 cosine of beta t, which is 1 times t, plus c2 sine of beta t. Sine of 1t, right? Because beta is 1. All right. So that's the general solution. Like I said before, like with all differential equations, you may have initial value problems. Always remember the initial condition is dealt with at the end. Once you're done with finding your general solution, you can proceed and impose the initial conditions so you could find C1 and C2. Now, in the second order case, you have to be careful with your computation, because notice you have to plug in 0 for t into y, and then 0 into y prime. So we must take the derivative of y before we plug in 0 for t. And then we form a system in C1 and C2 that we can solve. So let's do it here. Actually, we don't have room here because we need the product rule. So let's do it here. Y prime. We need the product rule here. So we have 2 e to the 2t times this parenthesis. And then plus e to the 2t. And now we differentiate the parenthesis. The derivative of c1 cosine, that's minus c1 sine of t, and then plus c2 cosine of t. This is actually easier than it may look once you're done with the derivative. Plug in 0 for t right away. Don't simplify this stuff because most of the terms are easy, right? So remember, sine of 0 is 0. Cosine of 0 is 1. Right, so when you plug in 0 for t, keep this in mind. Also, e to the 0, of course, is 1, right? So let's take a look at the y first. What is y of 0? Right, so y of 0 should be set equal to 1. Well, if you look carefully, that's just c1, right? Because that's e to the 0, c1 cosine of 0, plus c2 sine of 0. This should be set equal to 1. Again, with some practice, you can do this in your mind, because this is just c1, right? This is 1, this is 0, e to the 0 is 1. And so, by the same token, y prime of 0 will be 2 e to the 0, c1 cosine of 0 plus c2 sine of 0. Go on, plus e to the 0 minus c1 sine of 0 plus c2 cosine of 0, and that should be equal to minus 2, the second initial condition. So take a moment to make sure you understand these substitutions and try to do them in your mind with fewer steps so you can save time. Y of 0 becomes just c1, right? So c1 equals 1, and see, this is 2 times C1, and then plus C2 equals minus 2. So I have already C1 equals 1 from the first equation. I can plug it in into the second. 2 times 1 plus C2 equals minus 2. And that gives me C2 equals minus 4. So C1 equals 1, C2 equals minus 4. So therefore the final solution of the initial value problem is e to the 2t C1, which is 1 cosine of t plus or minus 4, because C2 is minus 4 sine of t. And that's the solution. So before we move on to the third part of this lecture, namely this, the remaining case, the double real root, let's actually do, revisit the example from the earlier part, from the first part of the lecture, and let's just put an initial condition for that solution, just to see how the system in C1 and C2 looks like in that case. So remember, in the previous example, we show that the solution was, let's see, C1, if I remember correctly. Yes, it was. So the previous example was y double prime minus 5y prime plus 4y equals 0. So let's attach an initial condition to this. So let's suppose y of 0 equals 3. Yeah, and y of 0 equals 3. And let's suppose the initial velocity, for example, y prime of 0, let's say that's 0. Okay, so we showed last time in the previous part that the general solution for this equation was C1 e to the t plus C2 e to the 4t, right? Because R1 and R2 are real, 1 and 4. So again, just like the complex case here, we have to take the derivative before we plug in 0 for t. There's no product rule here to worry about. So y prime is C1 e to the t plus 4C2 e to the 4t. All right. And now we plug in 0 for t. So y of 0 becomes, well, e to the 0 is 1, so that's just C1 plus C2, and that should be equal to 3. And y prime of 0 is C1 plus 4C2, which is equal to 0. Use elimination when you solve these systems. It's the easiest thing. So for example, I can subtract the first from the second equation. C1 minus C1 is 0, and I get 4C2 minus C2 equals 0 minus 3. So that gives me 3C2 equals minus 3, C2 equals minus 1. Then plug it in any of these two equations. So let's say I do that, I plug it in into the first one, so I get, what do I get? C1 plus 4 times minus 1. Well, I guess I plug it in the second one. So C1 plus 4 times minus 1 equals 0. That gives me C1 equals 4. And then the final solution then is going to be 4 e to the t minus e to the 4t. So y equals 4 e to the t minus e to the 4t. All right, so this is the complex case, as I said, and the distinct real roots case. We're going to finish then the whole lesson with an example, with the third case yet to be discussed, the double real root, and maybe some other extra examples toward the end. More on this soon.